Yeah. For the clock. Hello, and thank you for joining me today. My topic will be the recovery of rare earths. This work is being done at the University of Nevada, Reno, under my advisor, Dr. Chidambaram. Now, rare earths have become increasingly important. In 2011, as the statistic says, 696 million rare earth metals were imported. And magnets, the specific focus of this is the starting material, comprised 1.7 billion, 90,000 tons annually in overall production on Earth. Specifically, dysprosium and neodymium are expected in the next 15 years to skyrocket in demand. A large topic today, of course, clean energy. They play a central role. And according to the US Department of Energy in 2011, we see that neodymium and dysprosium are the highest supply risk and highest importance to new clean energy. Now, this is just one sector. However, they are used all across modern technology. There was a point where, mainly out of Mountain Pass, California, the United States was entirely domestically supplied with their own rare earths. We even had production of the magnets here in a few companies in Arizona. Now, due to different mining regulations and the cost of labor that has increased, China is our entire supply. I mean, we're not talking about 50% primarily, we're talking 90% primarily. And that's the situation that the world in general is facing. Rare earths come out of China. They recently were successful in their bid to the Afghani rare earth deposits by offering to build an entire railway station, or rail system for the country that has never had one. Now, that's a bid we're not currently in a position to match. We're not going to. So we've reopened the Mountain Pass mine site. But as with anything, it's taking time to get up to their expectations. We're expected to get to 35% of the world's supply eventually. That date keeps getting pushed back. It was initially 2018, then 2020. Now we're looking at 2035. We're at about 18%. And given our consumption, that is nowhere near enough. This is a breakdown of the US applications and world applications of rare earth metals. If you can see magnets there at US, it's 13%. And by that same congressional report, we're expecting a 10 to 16% growth annually in demand for magnets inside the United States. That led us to this goal. Rare earth magnets, easy to get your hands on in large quantities, but a growing concern in the industry. And they do comprise multiple rare earths. There is specifically neodymium, dysprosium, and praseodymium inside. They're a great starter material. We decided to focus on that. The electrolyting process that we're doing, very simple. It's the oldest commercial industrial electrical process. Very simply, we're using the magnet as an anode. We are varying the cathode in a lithium chloride, potassium chloride eutectic, heating that up, running a current, and hopefully depositing one from the other. Very simple. This is a well-known process. This is not part of the research. This is the application of something that we already know very well. This is the glove box, and I'd like to pause to thank my lab mate, Gus Merwin, for building this glove box and having it serviceable, which is extremely beneficial to getting a project up and running, having all the equipment already. And that's the setup right there. The magnet on the end of a tungsten wire onto a cathode. Just to give you an idea of the scale that we're working with and the times involved, very simple process. We can go back to these slides if anyone would like me to later. Once this is done, the 2-hour deposition, I collect that cathode, cut off a piece, and use SEM-EDS analysis on it. The color there, I hope it's showing up, is showing the selective deposition between the neodymium, praseodymium, and chlorine. Now, we don't want that chlorine and the rare earths to overlap, because that would mean we're depositing a chloride. It's just simply sticking, not actually electrodepositing. The fact that they are in different areas was a good first sign. And using the EDS analysis, when we first did this fresh, we were receiving a large atomic percentage of chlorine. It was coating the outer surface. Simply washing that with water exposed increasing amounts of the neodymium. You can see the difference. We removed 43% atomic chlorine and exposed 23% neodymium. Now, I'm not going to make the claim that EDS is purely quantitative, but it does give you a general trend. And to further support that work, we used UV absorption. Taking that same cathode that had been confirmed to at least have neodymium present, used a wash of HCl. Now, this goal was to make that neodymium chloride again, because that's the standard that we had run in the UV absorption. As you can see, the peaks do match up. And to confirm that the neodymium chloride was coming from the reaction with HCl, we did a sulfuric acid wash, and we saw none of the same peaks. So it's another good confirmation that what we're depositing is the metal form of that rare earth neodymium. Using XPS, which is an extremely sensitive surface analysis technique, we were able to see peaks that we expected. There's neodymium peaks, 2 of them, dysprosium, and the carbon and oxygen, which you can sputter to remove, but this is a first scan, initially, again, proving that we have qualitatively deposited neodymium and dysprosium in their metallic forms. To go closer onto the regions, this is the multiplex on it, a smaller binding energy window to focus in on a single peak. And of great importance was this. Carbon and dysprosium have a very similar binding energy from this. We were able to separate those peaks and give the supporting evidence that they're not a shadow of one another, but actually the different peaks. And we are seeing the dysprosium that we were hoping to see. Now, up until this point, all we'd been doing was qualitatively confirming that we had taken neodymium, praseodymium, dysprosium out of that magnet form and deposited onto the cathode. In order for this work to move forward, we're going to have to prove that this is a process that's efficient. So this is just a quantitative analysis done on a piece of neodymium, iron, boron composite that we got, not an actual magnet, because the magnets themselves did not come with their confirmed composition. This was confirmed by ICP analysis to have exactly 32.62 atomic percent neodymium. So I could try to build a calibration curve from this. All that we can glean from this is, yes, they're consistent with the spectra and decreasing with the assumed ppm. And when we look at the calibration curves that we got, that first large peak, the R-squared value is 0.978, the second, 0.979, and the third, 0.9835. Now, we're going to want to continue attempting quantitative methods, but this will give us a good idea. First, you're going to want to increase that R-squared value by a bit on that line. However, to continue the work in lab, this is a fairly accurate technique. It will give us a good window of whether what we're doing by changing different variables is increasing or decreasing the yield of that electrodeposition. If we're talking about an application for industry, you know you don't want to see efficiencies anywhere below the 90s. That's just not something they want to hear. However, given their rare earth's importance in defense applications, if it is a workable process, regardless of the efficiency, if we were to, for some reason, be cut off of our supply from China, because as we all know, competition for resources can strain even the most friendly allies. I wouldn't characterize our relationship with China as that. Would they attempt to cut off our supply in a terrible series of events? As long as we had the ability to reprocess the stores that we have, and as we saw, 90,000 tons are being made every year. If we can have access to that, which we currently do not, I can't stress that enough. Once these rare earths are used, there is no commercial process to repurpose them. And with the disposability of electronics certainly increasing and not decreasing, this is a vast store that we need to take advantage of. So the fact that we can say, I'm getting this much, that would be at least of interest in defense applications, if not commercially viable. As I was saying, the future experiments, you're always going to want to vary temperature in most of the processes we've been discussing in this course. The lower the temperature, the lower overall cost, the lower the materials cost. This is going to make it more attractive no matter the process. But specifically, we've had the issue of molten salt evaporation. When you go to the higher temperatures, specifically over 700 degrees, you can evaporate that 50 grams of eutectic in under an hour. You do not want to be releasing that much chlorine gas. That is not a good idea. Keeping it as low as possible, and we have done experiments at 400 degrees where the eutectic is very stable, less than 5% mass loss for 4 hours. And that, if that is going to be a successfully, highly efficient process for depositing the rare earths, that's going to be a huge advantage. There are other processes right now in the research stage to try and recycle specifically neodymium, but what they involve is the vaporization and condensing of magnesium metal. The energetics for that are not favorable. That would be the most extreme case of having to use this for defense applications. It requires a tantalum crucible. This is not going to be commercially viable. The simplicity of our process is going to be of a huge advantage to the other successful research that is currently going on. And you'd like to vary the voltage. In electrowinning, you have the ability to control very few things. The eutectic you're using, the cathode, the anode, and the energy putting in. By varying the voltage, we can attempt to selectively deposit out the neodymium, the dysprosium, the praseodymium, all while attempting to leave the iron alone and on its original form. We are at voltages higher than iron should be depositing, but we are at temperatures so low that iron's proving to be rather stable. Luckily, we weren't anticipating that, but that was a problem that we thought we were going to have, and we fortunately are not encountering, which is a vast advantage. So as this work demonstrates, there is the ability in these molten salt systems to simply deposit rare earths without the iron deposition. And we can use this with commercial disposable electronic magnets as the supply. Those are 2 large hurdles, and now the process of determining the efficiency overall of this experiment begins. If that's successful, then we move on to quite a different level of curiosity. This could be an applicable process not only for industry, but again, defense. So I thank you for your time, and I'd like to acknowledge my lab mates, most of whom are here. As I said before, Gus has built the thing. That was immense work. AK, Ruchi, Sanjeev, David, Darshini's not with us. Thank you so much, and to my professor as well, Dr. Chidambaram. So if you have any questions, take them now.
So, I was looking at the uses for these rare earths, and I was noticing that, of course, with catalysts, I'm sure they're essential, but you use it for polishing. Is there nothing else you can use for polishing besides these particular rare earths?
I haven't looked into how they're used, polishing-wise. 17%.
70% is for polishing. It seems like you could probably use something else.
That's very large. I would imagine it's a really high-tech aspect, and there's a certain, I know that their magnetic properties are particularly useful, which I couldn't quite figure out how that would go into polishing. But given their spike in price, it's got to be because we do not have something that can do what it does. I don't know what that is. I did not look into the polishing aspect, but given their price, to be used in such quantities, they've got to provide us with something that simply can't be substituted.
Have you looked into how hard it's going to be to try to pick out dysprosium from neodymium from praseodymium?
That we have not done.
How do you do that?
That, unfortunately, is traditionally done by the most ancient of metallurgical means. Melt them, they separate. We'd like not to do that. However, got to get over the hurdle first of, are we getting 0.01%? We're just seeing some neodymium and dysprosium. If we're getting in sufficient quantities, then particularly varying the voltage will become important, because best case scenario, run it at this voltage, selectively get out neodymium, change out that cathode, run it at this voltage. But we haven't, the only work done on that is for mining, and what they do is just simply melt slag and take off at separate levels. Thank you very much.